Okay, we also did derive the 2D elements. Okay, so one of the key challenge there was in the formulation of the finite element. So you might want to use the physical space variable. 所以呢，你们之前学的就是有些元素都是根据你那个这个 global coordinate， 就是说，然后我们来推导，但是实际上呢，你很可能你用的是一个 local coordinate。So you may do the displacement interpolation using your absolute coordinate. So take, for example, you may start origin from 2 to 3 for the length. But here in the formulation, we usually prefer starting from 0 to L as a length. So this kind of the spatial coordinate was what you did for derivation of the finite element formulation. But in the 2D space, so every point may have a different starting point, x1, x2. Okay? So in that case, so sometimes we prefer to use the variable, okay, that define with the coordinate starting from 0. So then we have the idea of changing the variable. Okay? So this change of variable would indeed affect the integral. So previously you can see that if this is the inverse line, so you may start integration from A to B. Okay? But once you do the conversion of the functions into another function and you change the variable, so your integration will start from beta to alpha or alpha to beta. So it depends how do you do. Okay? But in this case, so the introduction here is whenever you have a chain of variables, okay? This chain could be just a translation. This chain could be proportional chain. Okay? So and even you could have the nonlinear chain from linear to cubic or from cubic to linear. So long as you change the variable from x, y to ub, then the original function is not just the original integral is not just the original function's integration. You have to take the chain function, multiply with Jacobian, and then integrate with respect to the chain variable. 所以我们现在看到没有？如果说你现在是一个函数，它是往下降的，然后你通过这个函数的这个变量转换，把它变成线性。这个过程中，你如果说积分是算它面积 ，OK， 这个线底下的面积要跟转换过后的面积维持一样 ，OK。但是因为你的函数已经换了 ，OK， 你函数是 AB 了，你可能已经换成是U 了。这个时候，这个 x 转换成 U 这个过程，所以你这个转换过程中，你不可以直接把你的转换的变量带到你的函数里面，直接对 UV 做积分，因为它积分出来可能是一个值，但是跟原来的面积可能差一个倍数。所以这个倍数就要乘一个值，这个值就叫 Jacobian. Okay, if you know how to write the x is basically the x over the u times the u. So this is a chain rule for differentiation, very simple and direct, but graphically it's not that straightforward. Okay, it's changing the variable. So a nonlinear function can now become a linear. And the integrand area will remain the same, provided you pre-multiply the integral with respect to the x du. The x du is then the Jacobian. Okay? 所以刚才讲的是一维的，二维的Jacobian怎么取呢？二维的Jacobian你就要拿一个行列式来取。 how do you do the 2D transformation from xy to uv? Okay, if you want to calculate the function over the area， 好，我们来看一下刚才讲的面积，然后现在算的是什么？So the transformation of the function here will become uv to be like this. So you write this function, let's say function xy dx dy. Okay? So this will be the, or even if you do the 1d1, this is simply the area. And if you do the 2d1, this function is fxy. The coordinate is x and y. So if you have these chain of variables to channel this variable over this space. Okay? 所以同学看到没有？我们现在找的是什么？我们现在找的是一个体积。这个体积可能是从原的现在变成八了。OK， 那体积不变，不变的前提是什么？你要乘上一个Jacobian。OK， 就是 del xy over del uv. So this Jacobian for the 2D case cannot be written as del x del u, del x del v, and then del y del u, del y del v, and then you take the determinant. So this is then the factor. So we previously used this simple example to show you that this transformation will have this inclined parallelogram transformed into a rectangle. Okay? So our function is a constant value 1. But once you do this transformation, by changing the variable to be u and v, okay? And now you are taking the line, red line projected into the horizontal line, and then the height is chained as well. So this chain of variable will then give you the same area. Okay? Provided you, after you change the variable, you have to pre-multiply it with the Jacobian. So this is the chain variable. U is equal to x, v is equal to 2y minus x. Okay? So what is the Jacobian there? Okay, if we want to find the xy in terms of uv, you can readily do del x, del u, del x, del v. This is provided you do the transpose. OK， 所以我们在求这个Jacobian这个过程中，我们一定要把这个式子写成 xy 等于 uv， 你才可以做 del x del u 的微分啊。OK， 这是一般的做法。但是如果式子给你是 u 等于 x，OK， 这样你要怎么去找Jacobian呢 ？OK， 你如果要用 u 等于 x 来找Jacobian的话 ，OK， 你可能就要转字。Okay, in this expression, it tells you one important message. Rather than finding del x del v or del x del u, because the given expression is u equal to x, v equal to 2y minus x, this given equation can be easily written as del u del x, not del x del u. 看到没有？如果给你的式子是 u 跟 x 的关系，而不是 x 跟 u 的关系 ，OK？ 你如果要去做偏微分的话，这是最简单的。And then likewise, your del v del x is equal to -1, and then your del v del y is equal xy relationship, it's easier to write del u del x. Okay? So that raises to different way of calculating your integration. Okay? So I will add one extra slide. 好，如果给你的是这个关系 ，OK， 你比较容易找的是。Okay, given you this relationship, okay, the easiest expression you can find is this. But this doesn't make the Jacobian you want. Okay? Why we say it doesn't make the Jacobian? Because for Jacobian, you want del x del u. Okay? So here what you have is the inverse. So this is not the one we want. Okay, you want this, but what you have, the information here is not available. Okay. So you have this expression, which is only enough to find del u del x, del u v and del xy. Okay? So it's incomplete. Okay? So let's come out the finding here. Okay. So let's come to this transformation of Jacobian. Okay? Okay. So we can extrapolate the physical coordinate using shape function given the northern point. Okay? So this is a coordinate. Okay, we don't use x, y directly now. Okay? So in this case, you can find del u, del x to become del u, del psi, del x plus del u, del eta, del x. Okay? But here, the strain cannot, you can write this del psi, del x, del eta, del x. Okay? But look at your given coordinate and shape function. Okay? So this is not available. Okay? 你看到没有？现在假设转换的时候，我们要看一下我们手上有的 形状函数，它是 x 写成形状函数跟节点上的坐标。你要去求 del psi del x， 我们这个上数式没有办法给你 del psi del x， 它只能给你 del x del psi。OK， so as a result, what do you do? What do you do? You are writing del u del psi, okay, in the calculation. In this case, del u del psi is a variable, okay, because psi and eta is now your net function. Okay, let me just show you the net function, okay? In the 2D case. Okay. We're going to use the triangular element now. You have not 1, not 2, and not 3. Location x1, y1, x2, y2, location x3, y3. Okay? So if you are going to find the point, okay, in the coordinate, in the triangle, how do you find the point? This is my arbitrary point. How do you define the shape function n1? You can remember what is the shape function n1? This is shape function n1. It is this area. This is p2, 3 divided by 1, 2, 3. 形状函数的这个形象，三角形元素里面最简单的形象就是它这个点跟对边形成的面积除以总面积，就是你的形状函数。OK， 如果你没有办法想象，你可以把它画成例。OK， 这就是你形状函数的梯度，这个梯度刚好过着等高线。So how do you visualize the shape function n1? Shape function is 1 at point 1, but 0 at the opposite end. But if now I have arbitrary point, I want to find the shape function. Of course, I can go back and do the calculation using complex variable. Okay, but the easiest and simplest visualization is at that point, which match with the iso height. Okay, that should have the value of this opposite small triangle, sub-triangle, divided by the whole triangle. Okay, so how about the other shape function? If now I'm talking about n2. Okay, if I'm not talking about n2, n2 is 1 at point not 2, but it's 0 on the opposite end. So this point P should have a shape function n2 corresponding to the isoline P13 divided by 1, 2, 3. That's the area, the projected area. And last but not least, I'm now drawing my n3. Okay? This isoline match the 1 for P. My n3 is then my P12 divided by 1, 2, 3. OK， 所以同学形象上听得懂吗？不是要写公式而已，你要是形象上了解你的形状函数它的意义。OK， 虽然都是内插啦，如果你得形象知道内插的那个差别。OK。 of the shape function. Here I'm not going to have the shape function in just partial coordinate. I define this now as sine, theta, and then the last. Okay, are you going to use it? For 2D coordinate, this is simply 1 minus zeta, 1 minus sine, and 1 minus theta. Okay? So as such, you see, rather than finding the strain, del u del x, now you can differentiate the displacement with respect to natural coordinate. 所以之前是实际坐标，但是我们现在把形状函数当成是我的坐标，所以我这个形状函数当成的坐标，我叫自然坐标。OK， 它基本上就是0跟1之间的这个分野。OK， 所以你的应变不是 del u del x 了，我现在是讲应变了，就自然应变，所以就变成 del u del psi。OK， 或者 del u del eta。So now because everything is expressed in terms of shape functions. Okay, your coordinate change from physical coordinate to natural coordinate. Physical coordinate can be 1 to 5, but now natural coordinate can only be between 0 to 1. Okay, so now your physical gradient can be re-expressed as natural gradient. Okay, of course, you got to pre-multiply it with the chain of the natural coordinate to return back your physical gradient. Okay, but now we just take the natural gradient. It is del u del psi. By taking the chain rule, del u del psi can be expressed as del u del x and del x del psi plus del u del y plus del u del eta. And then also the coordinate in the y direction can be taken to be part of the coordinate, the gradient in the eta direction. This del u del eta is then expressed as del u del x del eta, and then del u del y del eta. Let's express these two chain rules into vector matrix expressions. So now the two natural gradients are del u del psi del eta. It can be expressed as a product of Jacobian with respect to del u del x del u del y. This is not really you need the inverse Jacobian for that. Okay? So because of these transformations, okay? So now you see this expression Jacobian can be obtained directly from the interpolation of your physical coordinate. The x del psi is the explicit expression. Del y del psi is also explicit. The x del eta, the y del eta also explicit. Since it's explicit, okay, look at our shape function previously. Your shape function x, y, okay, can now be expressed as x3 eta x13 and then eta x23. How do we get that? Okay, we get that from our previous interpolation. 还记得你的这个 x 怎么写吗 ？n1 x1 plus n2 x2 plus n3 x3. I tell you this is my shape function sine eta, and then this is 1 minus sine 1 minus eta. This expression is obtained because n1 plus n2 plus n3 is equal to 1. Okay, because of this, now I can do the simplification. So this is then, where do you got your constant term? Constant term is x3. And then the other two terms you have is psi term. Psi term is now having your x1 minus x3 and then sine. We write the short form x1 3. Okay, and the last term is a eta term. Eta term is your x2 minus your x3 eta. So we write a short form. This is your x23. Okay? Likewise, you can write the same for the interpolation of vertical coordinate. 所以我们现在空间上的坐标要完全用自然坐标来表示的话，所以你的这个式子你是用了节点坐标，然后再乘上形状函数，然后你的形状函数特别是 sin 跟 eta， 在 x 方向可以这么内插，在 y 方向也是这么内插。Okay? So now, after you have this definition of x and y, okay, it's really easy to write del x del sine, del y del sine, del x del eta, del y del eta, and this is then your Jacobian. This Jacobian is basically first row, first column x13, first row, second column y13, second row, first column x23, second row, second column y23. So by taking the determinant of this, then you have x13, y23 minus x23, y13. This is 2 times your area. Okay? You see that? Your Jacobian is 2 times the area of the triangle. Okay? So finally, we are not stopping at the natural gradient because you can't use the natural gradient to calculate the strain energy. Okay? This natural strain won't be useful. So what you need is now to find the del u del x and del u del y. To find this, you are applying the identity between natural coordinate and physical coordinate linked up by the Jacobian. Okay? And you can take the derivative of the u with respect to the coordinate. This is an obtainable value. Okay? 刚才我们做的那一餐是空间场上这个坐标的那一餐。OK， 然后我们现在再来是位移场上的这个那一餐，给大家记一下。Okay, now what is your u? Your u can be expressed now n1 u1 plus n2 u2 plus n3 u3. This is nothing but sin u1 plus eta u1 u2 plus 1 minus sin minus eta u3. So your expression is u3 and then plus this u1 minus u3 sine plus u2 minus u3 theta. Okay? So can you find del u del sine? Del u del sine can be obtained readily. This is u1 minus u3, and then del u del eta can then be expressed as u2 minus u3. Okay? Because these gradient of displacement with respect to natural coordinate can be obtained as that easily. Okay? Now this is a variable. This is a variable value. The Jacobian was also obtained as the gradient before. Okay? As such, okay, now your vector identity, vector of the natural gradient is equal to Jacobian times the physical gradient of the strength. OK， 所以我们现在是空间场上的这个实际的应变，要跟这个自然坐标场上的这个应变来一个转换，转换的结果是什么？你空间场的应变要通过 Cramer's rule 这个式子，才能从自然场上的这个自然坐标上的应变找出来。So now you are able to find the strain gradient, the displacement gradient from natural coordinate to the displacement gradient in the physical coordinate. So this is troublesome and very involving, but at least you now know you are able to do the inverse of Jacobian. Okay? So you don't need to do that calculation anymore. Because what you can handle is just pre-multiply the identity with the inverse Jacobian. Then you'll be able to convert the gradient with respect to natural coordinate to gradient with respect to the physical coordinate. Okay, in that way, okay, yeah, here I show you the example how to find the Jacobian, okay, and how to find the natural coordinate. Okay, so once you have this, now we can do the substitution of the expressions back into your energy equation. So, as you can see now, the physical gradient in the x and y direction and the shear gradient is simply del u del x, del v del y, and del u del y plus del v del x. Okay, it can now be re-expressed all in terms of 1 over the determinant of the Jacobian times this expression. Okay, 这看到没有？所以你现在找到的基本上就是刚刚我们求的。Okay. So after doing the simplification, in the end you find that this displacement gradient in the physical coordinate is just like what we did right. It's just as with what we did right. Okay. 所以我们做了这么大的功夫，就跟我们之前用空间场直接算应变是一样，感觉好像是费了很大的功夫，但实际上这个用处是之后在比较奇怪形状的这个。So why you need this mapping? So it doesn't seem that it's wise to do that since all these isoparametric formulations will give you the same expression, okay, as you derive using the physical coordinate. The usefulness of this will then appear when you try to handle the quadrilateral equation, quadrilateral element. OK， 所以你们已经用过2维的这个 ANSYS， 它自动给你的元素是一个四边形元素，它不给你三角形元素的。三角形元素之所以不行，是因为它把那个应变场当成是一个阶梯，一个元素就一个应变值。OK， 但是你如果是这个四边形元素，你的应变是从高到低是线性分布的，所以会比较准。OK， 所以你如果要算应变 ，OK， 你要用四边形元素。你如果在意的只是位，那个三角形元素也还好。然后一般有2派人嘛，一派就像这个画图软件 SolidWorks 或者是 AutoCAD， 他就跟你讲，空间上要塞得满元素，只能用三角形。OK， 那是站在填空的角度。但是另外一派是 ANSYS， 你要算得准应变，你就要四边形元素。 三角形元素只是去塞牙缝的 ，OK， 哪里不满才塞三角形 ，OK。So now you realize that why last week when you try the ANSYS, you managed to do the second part 有做第二部分吗？那个用 ANSYS 的部分，还是你们只停留在 manage？ So do you manage to try the ANSYS? Okay, good. You have tried the ANSYS, then you should realize that default there are no more triangular elements. They're qualitative triangular. But here I'm proposing you these formulations just to give you a flavor. What happened inside the formulation of the finite element? So now, what you see? Okay, we go step by step. Previously, we can obtain the finite element from the total energy expressions. This total energy expression consists of strain energy, density, integrate with the volume. 所以应变矩阵乘上这个本波方程的向量，这个应变的向量乘上这个材料性质的矩阵，再乘上应变，你得到的是应变的密度，再乘上体积，最终才得到应变。OK， 然后外力做的功有什么力？ So the total energy is expressed as a strain energy minus the work done. What are the work done? It can be done by a point force. Point force must be multiplied with the point displacement. Then you got the external work. And then you also might have what? You might have the traction. Traction is the tension. It's a line force. Then you must multiply it with respect to the displacement along the line, and then integrate along the line. This is the traction force. And the last term now you have is what you call body force. Okay, body force is like the gravity. Okay, it must be multiplied with the body displacement. Okay, and then integrate with respect to the volume. So these are the three external work done: body force, line force, and point force. Okay. So we have this. Then next, we are going to differentiate the expressions. Okay, with respect to your Okay, this we focus now on this strain energy. Okay. This strain energy previously was integrating with respect to the volume. And now because you change your coordinate from xy to the natural coordinate. So your xy is changed to sine and eta. Your x and y could be a physical range between 1, 5, 1, 3, 3, 5, or whatever. But now you all change to natural coordinate. Natural coordinate can only be bounded between 0 and 1. Okay? So that kind of mapping is possible. The product of the natural coordinate change is pre-multiplied with the Jacobian. Okay? So now your strain energy expressions is expressed in terms of the natural coordinate. Okay, and then next, given the same expression for the strain energy, now you take the differentiation of the strain energy with respect to the displacement, northern displacement, then you are going to obtain the northern force. Okay, 我们是双管格式，所以我现在仅只用这个简单的这个矩阵向量相乘来简化。So eventually, you obtain your element stiffness matrix, which is the gradient vector, the gradient matrix times B matrix times the gradient matrix, and then integrate with respect to the volume. Okay, so this is then your stiffness matrix. Okay, so that's the part for the isoparametric formulation. Okay, now we come to the gist of the 2D rectangular element. Okay, from the first day when finite element formulation has been invented, okay, by this American civil engineer, okay, so people have been extending these from linear function to quadratic function, from triangular element to 2D polyhedral element, from 2D element to 3D element. The formulation method is the same, okay. 所以我们自从这个有了第一个二维的这个有限元素的这个推导的方法过后，它这一套方法就一成不变的被应用到二维三角形元素、二维四边形元素、三维三角锥元素、三维这个六面体元素 ，OK， 都是这样的延伸 ，OK。We'll see that. Okay, what happens if you now have a rectangular element? Okay, to make the formulation easier, then we set the center line to have the coordinate 0, 0. And then the width of this rectangle to be 2b. The height of this rectangle to be 2h. Okay, this is the rectangle we consider. Given this northern coordinate 1, 2, 3, 4, the coordinate is minus b minus h, plus b minus h, b h, and then minus b h. These are the northern coordinates. Corresponding to that 4 knots, you define the 4 displacement. You have u1, v1, u2, v2, u3, v3, u4, v4 in the x and y direction respectively. Okay. Now, in order to do the interpolation, because you already have the full 2D element, so then you're going to have expressing your displacement chain as a linear function, not quite yet, plus a nonlinear term. This nonlinear term is a product of x, y. Yeah. 所以你们现在你要做内插的时候，虽然你想把它的这个位移场的变化当成是一个线性方程。OK， 之前三角形元素 OK， 但是现在是四边形元素 OK， 所以你要多一个节点 OK。所以要多一个节点的讯息，你不能把它丢掉 ，OK？ 所以你的这个内插的这个函数，你就不能再用 x y 了，你要多加一个函数项，就是 x 乘 y，OK？ 所以有4个节点，你自然要有4个未知数，这样你才会做到比较好的这个内插 ，OK？So likewise, you do the same interpolation. For vertical displacement. Now, your interpolation rely on the coefficient v0, v1 times x plus v2y plus v3xy. So the coefficient v0, v1, v2, v3 are to be solved. Okay? 所以你要怎么找 v1, v2, v3？ 很简单，首先把节点1拿出来，代入函数 ，OK？ 如果是已经代入的话，同学不清楚，我们再重新解释。So you got to clear how to do substitution of the northern condition. So you write the interpolation. You now have your this coordinate u equal to a0 plus a1x plus a2y plus a3xy. Okay, this is the interpolation function you have. And now you take the northern condition. Knot 1 is located at minus b and minus x. It has displacement u1. So substitute in this condition, u1 is equal to a0 minus a1b plus minus this is the first point, the first equation. Then next, you write the second normal condition. This normal condition is normal coordinate 2 has displacement u2 is located at plus b and minus 10. And then this u2 is then equal to a0 plus a1b, okay, minus a2h minus a3bh. Okay, you repeat the same normal condition to knot 3, to knot 4. Okay, then you're going to have a 4 variable a0, a1, a2, a3 to be solved. This related to normal condition, not 1 displacement, not 2 displacement, not 3 displacement, not 4 displacement. And these matrices, okay, is just a coefficient. This is 1 times a0 minus b times a1 minus x times a2 bh times a3. And then how about the second row? Second row is 1 times a0 b times a1 minus h times a2, and then minus bh times a3. And likewise, for the third equation, you have 1 times a0 b times a1, and then your h times a2, and then your bh times a3. And then the last equation, when you transform them into the matrix form, this is 1 times a0 minus b times a1, and then h times a2, and then minus bh times a3. Okay, in that way, now you have the 4 simultaneous equations, and then you can still solve this by Cramer's rule. Okay? 所以我们相当的懒，就是基本上用 Cramer's rule 一招解决完。但这一招你会解吗 ？Okay. So how do you solve for the Cramer's rule? Okay, let's try to do that. Okay, this is what you have, huh? Okay, I copy down first. Okay. So this is your a0 is equal to u1, u2, u3, u4 minus b, b, b minus b, minus h, minus h, 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 b. What's that? This is the bh, right? This is minus bh, then this is bh, this is minus bh. Okay, 我们就不看这么多，我们先教同学怎么解。OK， 或者是分母部分。分母部分会解吗 ？Okay, this is the expression for the determinant. So I copy down 1, 1, 1, 1 minus b, b, b minus b minus h minus h h h b h b h b h minus b h. OK， 好，抄完之后我们再来对。给老师这一招是跟当年这个老外在文艺复兴的时候怎么作画，那个老外就是做写实画，你知道吗？有投影机啊，然后你就照着学 ，OK。所以老外是画写实画。Okay, now let's do the practice. How to find the determinant? Yeah, it is short of the battery, so I can switch off. Okay? Okay, how to find the determinant? Okay, you need some practice. What is the determinant? The simplest one you have is you can factor out B from one row. You看这受影响的这个负一，行列式还记得吗？你可以把这个公因式拿出来。下一个呢，到超过的 second row， so we going to factor out the head. So we have minus 1, 1, 1. And then the last term, we factor out the B head. So in this case, now you have 1, minus 1, and then 1, minus 1. Okay? How do you solve your determinant? To solve this determinant, you need to take one row times the cofactor. What is the cofactor here? So it's a little bit troublesome. Okay, it's 1, 1, minus 1, minus 1, 1, 1, minus 1, 1, minus 1. And then plus, second term will be minus 1 times the cofactor. What is the cofactor? The cofactor for this item is the one that not passing it. So this is the second cofactor. This is 1, 1, minus 1, 1, 1, minus 1, 1, minus 1. Okay? And then how about the last, the third one, the third cofactor? Plus minus 1, which is now plus minus 1 times the cofactor. What is the cofactor? The one not passing the row. Okay? You have your 1, 1, 1, 1, 1, minus 1, and then your minus 1, 1, minus 1. That's not the end. The very last, let's see. Where's the very last? This is minus. Minus 1 times the minus cofactor. Okay, this is 1, 1, 1, and 1, 1, minus 1, and then your minus 1, 1. Okay. 好，同学看懂吗？所以为什么大考让你们用 Method？OK， 不然题目能出幼儿园的题目。Okay. So that's why you see this is how you operate by hand. Okay, that will be too tedious. Okay. Okay. So by doing that, okay, we eventually find out a simple expression. Okay, so your A naught is the sum of U1, U2, U3 times minus 4 divided by minus 60. Okay, after you do a very hard work doing the generation, no worry, you do not need to derive that. Okay, so then your A naught is the sum of the 4 displacement divided by 4. You if you do the same, okay, anyway, this is side work. You have to show you how hardworking you are, okay, to finally derive, okay. So that's done by the finding of finite element. It's really hardworking, doing step by step in the days where computer is not available or not available at that time. At least to him. Okay. So in summary, so you eventually use a Cramer's rule to find out your A0, A1, A2, A3. These are the three coefficients that let you to do the interpolation or coordinate to the displacement. So your A0, A1, A3, okay, are displacement divided by displacement sum, displacement difference, and then divided by 4BH, okay, or whatever. Okay, eventually, if you do the re-expression, okay, did you spot any error in the expression here? Did you spot the error? 同学看到这个公式，哪一个有错？1、2、3、4，哪一个公式是错的？ A2 must be wrong because A2 is the one corresponding to the height. Okay, so this cannot be the this. Let's see this. So this is then okay. This product give you B, and this product give you H. Okay, so they are typos. Okay, eventually now you find the 4 variables. Okay, with this, now you can find U is equal to a row vector times a column vector. This row vector is 1x, y, and xy, and this column vector is now expressed as the 4x4 matrix times the 4x1 vector. Okay, in that way, if you do the expansion, okay, you're going to have these interesting expressions, but now we group the coefficient by nodal displacement. So rather than arbitrary grouping, we now group whichever associated with nodal displacement 1 as one group. And the second group is associated with nodal displacement 2. And then the fourth group of the coefficient is associated with the nodal displacement 3. And then the fourth group is associated with the nodal displacement 4. 所以我们这一串乘出来非常的乱 ，OK， 但是我们是根据你节点位移来组合。第一个组合是什么？第一个组合就是你的形状函数嘛。所以 if you do proper factoring of the expression, the first coefficient that is a shape function for nodal 1 will then be x minus b, y minus x. Okay? So you may not know what is the shape of the shape function. Okay? But you know that shape function must be 1 as a local form. 就看到你的式子长得再复杂，它的形象上它应该要满足这个条件。如果你这个就是 n1 形状函数1 ，OK， 它在节点1上面就应该是1，在 在它的对边，所以你现在搞的是一个金字塔，那不是三角锥，这个叫怎么锥呀？这个锥叫什么？四面体 ，OK， 是四面体吗？1、2、3、4，有没有？金字塔。OK， 就是你可以把它当成金字塔。Okay, so now this shape function become a pyramid. Previously, the shape function looked like a tetrahedron. Okay, so this is a section of pyramid which has the value of 1 and not 1. So meaning, at not 1, okay, what is the not 1? Okay, you may forget the derivation, but you cannot forget the shape function geometry. Okay. So for this coordinate triangle, what's the coordinate? Center is 0, 0. Not 1 is minus b minus h. So now we draw this in 3D. This shape function at minus b minus h is equal to 1. And the other point is 0. Okay? So what is this shape function? If you write this, n1 is 1, provided is minus b minus b minus h divided by 4bh. And write the same. Okay? So this expression is now x minus b, y minus h. So that it is 1 when x, y are minus b minus h. OK， 看懂吗？这形状还是非常好记。OK， how about does it becoming 0 at other point? Okay, if you now have b in the expression here, this is the location here where it comes to the b. This term is going to be 0. So this one is 0. Okay? And even if this is not 0, but if your y, the height, is equal to h, okay, this point is 0. Okay? Along this line, this height is variable depending how far you are. Until the point that this is 0. So this is the way you see the shape function. Okay? And then next, we are looking at the second point. Okay, what is the shape function? Okay, so that is not 0.这个 n2 怎么写的？ n2 要写的话，它基本上是我们这个对它1的情况来写，它应该是这个 x 加1，然后负 h 看到它的样子就可以。So you can practice on how to write the shape function. And the third shape function is v hat. And then your n3 is then your x plus v, y plus hat divided by 4v hat. Okay? And then how about the last one? The last one is your minus v and positive hat. Your n4 is then your x minus v, y plus hat divided by minus 4v hat. Okay? So that's the same idea. You are using your coordinate information to force your shape function to be 1 and the local coordinate. Okay? So 作为工程师啊，你可以不会数学，但你不能不会看图。OK， 你出去的话，起码要能看图。OK， 所有的数学是从图里面推出来的。OK， 所以你跟电机工程师的最大优点是什么？你看得到三维的，他还活在二维。Okay, in this way, so you now have the shape function defined. Okay? So this is what you call bilinear shape function. Okay? So at node 1, n1 is 1, but at node 2, n2, yeah, n1 is 0. So this is typo here. Looking at the so how do you find n3? Yeah, please do the same. Okay, after you have defined the shape function, we will now repeat how to define the gradient of displacement or strain function. Okay, here we are not using isoparametric to avoid confusing you. We are still using the physical coordinate. The gradient in the x direction is then the derivative of the displacement with respect to the x coordinate. Then you now have the del n1 del x u1 plus del n2 del x u2 times del n3 del x u3 plus del n4 del x u4. We now do the repetition to define the strain in the y direction. For the shear strain expression is more complex, but it's nothing but del u del v, del u del y plus del v del x. So it's just an expansion. It's tedious. That's why you want to write them in the matrix times vector form. You can't handle that because it's too tedious. But you can readily view it and see it, to check it. The strain vector is now this gradient matrix times the northern displacement vector. This northern displacement vector got 4 nodes, each node got 2 degrees of freedom. So you have 8 by 1 displacement vector. And then your strain for 2D elements, you only have strain in the x direction, strain in the y direction, and shear strain. That is a 3 by 1 strain vector. So to link 3 by 1 strain vector with 8 by 1 displacement vector, now you need a matrix. This matrix has a size of 1, 2, 3, 3 rows. 1, 2, 3, 4, 5, 6, 7, 8 columns. So this matrix is 3 by 8 in size. Okay? So in short, the displacement vector, the strain gradient, the strain vector is now the gradient matrix V times the northern displacement vector. Okay? So you now have the interpolation and And then next you have the gradient. Now you have this expression. And then this derivative is simple. The derivative of the first straight function with respect to x, second with respect to x, third with respect to x, derivative of fourth straight function with respect to x. Now you have a derivative in 3 notes. Okay, and then doing the same way, you can define the strain in terms of straight function gradient times the respective order displacement. And then you do the same with respect to y. Okay, let me correct this. This is the derivative with respect to y.所以对 y 微分过后，所以只剩下 x 这样子。OK。How about the shear strain? Yeah, the previous one I leave it for you. Okay, only derive the simple one. Okay, in short, your straight function. Okay, after the gradient, after taking the derivative, now you have the B matrix expressed purely in terms of this expression. Okay, this expression is a linear function. It's changed with the space. 所以跟之前你们学的这个三角形元素有什么差别？三角形元素它的这个 B matrix。它是一个常数项，对，因为它的这个自然函数，它的形状函数对空间那个微分网络，它只是一个常数项，但是这个不是常数项哦，这是一个线性项。线性项的结果是什么？你要做积分的时候，这是比较麻烦的，你就会有二次项。OK， 不是单纯高度乘上面积就表示 ，OK， 它这个是有一个斜度 ，OK。So eventually you need Gaussian integral to help you doing the integration. Okay, so this is like finding the trapezoidal. Okay, why the integral here is difficult? Later we want to show you. Okay. After you have obtained the strain, you can find the stress. Then this is another product. D matrix and B matrix will give you this expression. And then how do you find the nodal force? Nodal force can now be obtained as the 3D, the volume integral of B matrix transpose and B matrix and B matrix over the volume. Okay? And then this will then give you the 8 by n matrices. Okay? So 8 by 8, then you got 64 elements. So it's only doable by computer. Okay? And the B matrix is this also 8 by 8. Okay? Of course, with the help of MATLAB, I repeat this. Okay, for C11 and C21 and C31. The rest is left to you or computers. Okay? Okay. So next come back. Why do you need to use the mapping? To do the mapping, the reason is I'm not going to just handle the 2D element. 2D rectangular element. I'm going to handle 2D quadrilateral element. So this matrix now, rather than using the physical coordinate, I'm using natural coordinate R and S. R in the X direction and S in the Y direction. Then my natural coordinate will have 4 knots. That 4 knot is very simple. -1, -1 for knot 1. And for knot 2 is going to be 1 -1. And for knot 3 is 1, 1. And knot 4 is -1, minus 1, 1. Okay? So then, what's the good thing about that? Since you're not handling the absolute coordinate now, you're handling the natural coordinate, your integral becomes very simple. 所以你在现在的变换，你现在是坐标变换，你坐标从 b h 改变成负1 OK， 所以这个时候你的变换，你的坐标就要完全用自然坐标去标示。So now your n1, n3, n2, n4, all expressed in this expression is now becoming 1 minus r times 1 minus s divided by 4 for shape function 1. And for shape function 2 is 1 plus r, 1 minus s divided by 4. Likewise, you can do for shape function 3 and 4. Now, the shape function still look the same like previously, except now the base, the coordinate, the northern point is now 1, 1. Okay, and minus 1. Okay? So it's different from the physical coordinate. So based on this, I can also do the interpolation using the same shape function for displacement in horizontal and vertical direction. And now I can do the partial differentiation. Rather than finding del u del x, now I'm finding del u del r, del u del s. Okay? Then you can do the inversion to finally find the del u del x. Okay? So this is the way how I calculate the del x del r, del y del r. Okay? By using this chain rule, okay, eventually you are going to do these transformations. Okay? So here what you see is not these. Okay, this is straight in the x direction. This is del n1 del x, but my n1 is in terms of r of s. So now I re-express the del n del r del r del x. Okay. So eventually you find this straight gradient. Okay, displacement gradient. So this time now the integration becomes easier because it is bounded between minus 1 to 1. Okay, so then this is the gist why you need to do isoparametric formulation. Okay, as an example, so to show you, now you have the square element. Would you be able to write the stiffness matrix for this square element? Okay, this square element is not square. I think I have to redraw that. So this is misleading. You see this as a square. Okay. Okay. Here look better. Look more realistic. Okay. Oh, it is indeed square. The question is indeed square. 不好意思，那题目的确是方形。It's really square. Okay, then yeah, please go back and practice. So okay. So now how do after you find the stiffness matrix, you can find the displacement, and then you can also evaluate the stress. Okay, the stress calculation is based on your these strain information multiplied with the D matrix. Then you construct that vector, and eventually you come to the final solution. Oh, so that's it for this semester lecture. So for the later half, then I'm going to go through with you some of the homework answers. 我们这个 就讲到这里，然后我们休息10分钟。We'll have a 10 minutes break, and then we'll come back again to discuss about the homework.